Okay, so before I start, anybody has got a MacBook charger? Because I probably am running out of charge. You have with you? Okay, if I run out, I'll just borrow from you. But for now, I think I'm good. Okay, so as I mentioned, today is going to be a mixture of a lot of things. I'll be finishing the neural network topic. Then we will have some hands-on exercise that we will do. And at the end of the lecture today, there will be like multiple guest speakers with like a lightning talks, like 5 minutes, 10 minutes kind of thing. So I'll tell you as the class moves on. But let's first finish our business, and then we will go from there. All right? Okay, so in the last class, we talked about how does the backpropagation rules work when we just have an output layer, single output neuron, right? And we said the gradient of the error function with respect to Wi looks something like this. TD minus OD, OD times 1 minus OD times XID, where TD is the label. OD is the prediction, and XID is the input. So you kind of have this nice formula where if you combine all of the other terms other than the XID, then that term can be called as delta, which is the error. And with a single output neuron, that's straightforward, and we have seen how to derive this. And then we said, like, what happens when we have hidden layers? Because in the hidden layer, we don't know what the error is. And we want to compute or estimate what kind of error was actually generated due to that particular hidden unit, and what should be the weight update with respect to that. And there we said we have some formula like this to approximate, because we said for the neuron for which we are computing the error, we can immediately see from the network like where the connections, and we can see for the subsequent layer, we can see what errors actually happened, and based on that we can do a weighted average of the errors and assume that that error was propagated by that particular neuron in the previous layer. So we already talked about this, and it turns out this assumption makes backpropagation possible and training of neural network possible, and that can do magic, as we already know. So we have gone till this point. So most of the technical parts are covered, but there are a few issues that we should discuss. So some properties or issues with backpropagation, right? So we are essentially doing gradient descent, but now we are doing over multiple layers and multiple units and multiple weight vectors, right? So, and then you can have arbitrarily large directed graph, which is called the network architecture, and you can try to train and fine tune that. You will get stuck to a local optima. It's guaranteed, but it's not guaranteed to converge into a global minima. Why is that? Although we have an error function, right? You remember? So we had the error function y minus function of x whole square. We know y equals to x square is a convex function, right? And then it always converges to the global. It has only one global optima. But here you have a function that is more complex. And depending on this function, there is no guarantee that there will be just one single global optima. It could be multiple. It could be a rough landscape like this. So wherever you start, depending on that, you are guaranteed to converge to a local optima. Maybe if you start from here, you will reach here. If you start from here, you will reach here, or something like that. But it's not guaranteed to go to global optima, and that's why you need to do multiple trial and error with random initializations and have to do some exploration tricks to actually find out a good solution. And then you could also, here is this trade-off that you have to strike, right? So you you want to explore the whole space. That means you kind of want to be random. You want to search here, search there, everywhere. But if you just keep doing that, if you go to that extreme of random exploration, then you will probably not converge to a solution that kind of is a local optima, or like even a local optima that is very close to the global optima, because you are just jumping around. The other extreme is you don't do randomization, you just focus on the local optima, where I am. I just want to go towards the definite direction that gives me a local optima, right? So it's kind of like, there is a well-known term in machine learning and AI for this kind of trade-off. This is called a exploitation-exploration trade-off. Trade-off. Exploitation means where you are comfortable with that, you just want to make minimal move to your next step. Exploration is like more wild. You want to explore at different places, right? Then you probably now see like both extremes are not good. If you just do exploitation, you are kind of stuck. You are not making improvements. If you are doing exploration, you are kind of doing random luck kind of thing. It's not informed based on what you have already achieved. So you want a kind of like a trade-off between exploitation and exploration. The right answer to what degree you want exploitation versus to what degree you want exploration is probably debatable, and there is no clear answer. And that's where your experience, your trial and error, your different experimental setups will help you. But it's important to understand that there is this trade-off that every machine learning model kind of tries to, because you are essentially doing a search. Any search algorithm has this trade-off. If you have a massive space, you want to do this trade-off of exploitation versus exploration to ensure like you have explored enough, but at the same time you have something that is something that is a decent solution. All right. So next, so you see this weight formula. There, you could. This is the term we have already seen, right? The gradient update, and you have a parameter called eta to control this. But then you can also have an alpha with the weight updates. And what this is essentially saying is your weight at iteration n should have some component of your weight that was in the n-1 iteration. So it's like, don't move randomly so far, even if you have a like large eta. Try to remember who you were. So kind of like in the previous iteration, whatever your value was, add some contribution from that value. So that this is kind of saying like, do some exploitation. And this is more like an exploration thing, because depending on larger eta, you could go very far. So there is and this thing is called momentum. So you are at a particular place, you are moving at a certain degree, certain direction, and don't just flip around and just go to some random thing. Add some momentum. There is some inertia to that direction what you were already going in. It's not like entirely flip don't just make a U-turn in the highway. That's the analogy. Okay. So again, the same question. You can minimize error over training data set, but it's not guaranteed how it's going to generalize. And there you can use all those tricks like k-fold cross validation. You can use validation sets and like multiple random initialization and so on. All right, so you have seen this plot many times. The point here is, although your training set error is going down on the top figure, it doesn't necessarily mean that your validation error will go down as well. You see, after a certain validation is going down, but then suddenly it again starts going up. So you want to find a solution that maximizes your accuracy or minimizes your error on the validation set, not just the training set. And then finding validation accuracy for is not always straightforward, because the curve could look something like this. If we just stop here, assuming, oh, right now I see some increment, so maybe I will stop here, then you will not get to this point. So it's not often clear, like once you start seeing increment in validation error, that doesn't mean that you have already got your solution. So you probably want to explore many different number of iterations, and based on your entire history, you want to make a call, rather than just saying like, oh, it was decreasing and just right now I see some increment in error, doesn't mean you should stop. Okay? Questions? Good. So dealing with overfitting, we already know how to do this, right? We split on training and validation set, and we perform training on the gradient set, but try to test on validation error and try to create those plots. There are other tricks that you can do for neural networks. For example, you can add some regularizer term, right? The norm constraint. The first one is essentially regularization. So you can try to impose L1 regularization in the loss function, or L2 regularization. That will try to make your solution like more general rather than overfitting your data. You could do dropout, and the dropout is essentially meaning you could drop some of the weights of the neural network and try to see if you can achieve the same performance. If you can, that basically means you don't need so many weight connections. You are just wasting effort, and those extra weights will probably try to overfit something. So you can try to get rid of a certain number of portion of the weights that you have in your network and try to retrain and see if there is a significant drop in the accuracy, right? So batch normalization is essentially within a batch, you can try to normalize your data so that the neural network every time is getting trained, see data that is within the range. It's not seeing something very different. So you could also try these kind of techniques. You could add more data to impose more constraints so that your model becomes more general. This is data augmentation. And then you can try to stop early as well. Well, if you stop early, then you don't know really like what is going to happen if you had trained like many iterations. So early stopping here basically means you kind of checkpoint your models as you go by, and then look back into the past and try to see if you had stopped at a particular early point, was your validation accuracy better, and then kind of take that checkpointed solution. Okay, so that's what early stopping really means here. Convergence, yeah, there is no guarantee. So you always have to explore, and no matter how many times you have explored, probably you cannot guarantee global optima. All you can do is to get to a convergence solution and then try to see how it performs on some downstream task. Do some classification, regression, and try to see what the accuracy is. So why neural networks are so popular? So the reason is they can express anything. And the reason, we will see some of the arguments behind that, not all of them. But the point is, any Boolean function can be represented by a network with a single hidden layer. So that's kind of something that we will show with example how this can be. And for continuous function, there are papers that tries to prove that if you have a bounded continuous function, that can be approximated with arbitrarily small error by network with one hidden layer. So one hidden layer kind of is already very powerful. There are papers, we are not going to actually read these papers, but the idea is we should know there are theoretical proofs that guarantees that neural networks can approximate almost every function, right? And then that is for bounded, and if you don't have a bounded function, any function can be approximated to arbitrarily accuracy. So see the difference between these two. There is an arbitrarily small error, and it's no longer small r. So it basically says neural networks will give you a function, but it will not give a guarantee with a smaller error or like a high accuracy. And that's actually true, because if your data is random, no model can predict this. And there is no guarantee. Nobody can guarantee you will get something useful out of it, because there is nothing to learn, right? So these papers, as you see, have already been coming around 1989, 1988, and at that time, probably around when I was just 1 or 2 years old, okay? But then you see the entire like field actually booming in 2015. So the only reason that this took a lot of time because of the scarcity of data and computation power and all those GPUs and all that. The techniques, the proofs, the theories were already there in the 1980s. So let's talk about why neural networks can approximate Boolean functions. So let's think about the OR function. What is the OR function? Let's not look at this. Let's discuss first. What is an OR function? Boolean OR. Yes.
At least one of the inputs is true, and the whole thing's true.
The whole thing is true, right? So if one of the input you have is true, then the output should be 1, right? So let's say your space is, these are all the variables you are dealing with, okay? And we are talking about Boolean variables here. So the OR function basically saying any of this x, if you take and take an OR, the output should be 1 if at least one of them is 1, right? And you can approximate this with a neural network with just this kind of threshold function. What you need to do is, first of all, you must have an expression, right? Which is, let's say x1 or x3 or x5. Let's say this is your function that you are trying to learn, or you are trying to actually approximate with a neural network. What you can do? You can use a network like this, where the weights that you see, just a single layer, it's a threshold function, and it's a threshold on a dot product, right? So what you essentially do is this. You have 2 inputs, actually 3, x1, x3, x5. But if you want to have a general representation, you should also have x2, x4 till xn, right? Because these are all your variables. You don't want to have a network every time. You just need one network for all the OR functions. Then the point is you have an output layer and you have connections, right? You have connections like this. So just for the OR function, you first look at what variables are there in my expression, right? Set those weights to 1, the rest of the weights to 0. Now you take a dot product and a threshold function. What happens? And the threshold, you need to define what the threshold is. And the threshold here is nothing but, and then you also have x0, which is the bias term. And I'll explain what that is, but the threshold is minus 0.5, right? So now think about one instance where, so first of all, because we have 0 weights here for the other variables, it doesn't matter what the input for x2 is, what the input for x4 is, they are ignored already. They are filtered out by the network, right? Now the only thing that this network cares about is x1, x3, and x5, because those 3 weights are 1. Now if you have a 1 in x1, 1 times 1 will become 1, right? And you have a bias term 1 that you are adding. So with x1 equals to 1, what you have is 1.1 plus 1, and you have a threshold of minus 0.5, right? Which is equal to what? 1 plus 1, 2, 1.5, right? Which is positive, so the neuron will fire and you have a 1 as output. If you have more 1s, then you have, let's say 3 of them are 1s, so you have more positive value, 3.1 plus 1 minus 0.5, 4, 3.5, which is even positive, and again you fire. So as long as one of them is 1, you will fire. But if all of them are 0, what happens? What would be the output of this neuron if all the inputs are 0?
1 minus.
Sorry?
1 minus 0.5.
1 minus 0.5, right? So this is just 0.5. So what we are saying is, if you have a threshold here that requires your value to be actually greater than 0.5, then you will not fire. Okay? So the whole idea is you will only fire because all these are like say 0, you are not adding anything here, and here you just add a 1, and you have a threshold that has to be yes, so your threshold has to be here at least greater than equals to 0.5. Yes?
Isn't it 1 into minus 0.5 like the input?
That is actually true. You're right. You're right. If you consider this as an augmented representation, if you multiply with this, and then in that case, your threshold doesn't even need to be 0.5. It could be just 0. In that case, what happens is you are essentially saying this is just giving you minus 0.5, which is less than 0, and then you are firing. So yes, you are correct. If you multiply, if you treat this as an input, and if you treat this as also part of the dot product, then you have a minus 5, and then the 0 threshold will work. But if you think of this as, I was treating them as an addition, which is probably not correct here, because you are kind of taking dot product, and if you also take dot product, then yeah, that makes more sense. I agree. So essentially you get a minus 0.5, and which is less than 0. The only time you will get above 0 is essentially when you have a 1 here, and 1 times 1 will give you 1, which is if you subtract 0.5 from here, you have a positive value that will fire. That's correct. So yes, so considering they are part of the dot product, this is essentially 1 times minus 0.5, and the threshold now you just need a 0 threshold. But the whole point is you can approximate OR function with a neural network. That's the point. So here you just set these values to 1, others to 0, and then you set a proper threshold. That's what you need in order to achieve. So similarly, you can do an AND function. And in that case, in the AND function, your bias term will just change. So again, you have this one input, and your bias term is 0.5 minus k. Now tell me what happens, and your inputs are again the same thing. The terms that are there, for which there you have ones, the terms that are missing, you have 0. So tell me what happens when, let's say, all of them are 1, x1, x3, and x5. If all of them are 1, what we are going to see here. And tell me first, what is the k here? So k is essentially the number of variables you have, right? So here you have 3. So if you subtract this 0.5 from 3, you get minus 2.5, right? So this is your network for x1 and x3 and x5. Now tell me, if all of them are 1, what is going to be the output? What? 0.5? Positive? Okay. Because you have a 1 here, you have a 1 here, and you have a 1 here. So you do 1.1 plus 1.1 plus 1.1. So you get like this, minus this bias term, which is 3 minus 2.5, which is equal to positive 0.5. Assuming a 0 threshold, this will fire, right? Okay, let's think about x1 and x5 are 1, and x3 is 0. What happens?
Minus 0.5.
Minus 0.5, right? Because one of them is now 0. So you get a minus 0.5. Does it fire? No. So if not all of them are 1, it will not fire. So this is essentially what AND function is supposed to be, right? You only fire when you have all the 1s. All of them are 1, right? And similarly, you could handle negations with minus 1 weights. So the whole idea is, if you have a minus in terms of x3, negative of x3 in the logic, then what you can do is, you will put a minus 1 here. And you will have a separate, a slightly different threshold, where t is essentially the number of positive terms. So x1 and x5, not this one, which is 2 here. That basically means you have minus 1.5 here. So the only time this neuron will fire when this is equals to 1, this is equals to 0, so not x equals to 1, and x5 equals to 1. So then you will have 2 plus 2, and then you will have you will have 1 plus 1 minus 1. So essentially you have a 1, and here you have 2 minus 0.5. Actually, you have minus 0.5 minus 2, sorry. So that basically tells you minus 1.5, right? Yes. So now you have 1 plus 1 minus 1, they cut out. You still get an output of 1, which is greater than minus 1.5. It will fire. But in the other cases, when, let's say, one of them is 0, x1 or x5, then you will never get this 1 plus 1 term. You already lose 1, and then the other part becomes 0, minus 1. So you will essentially get minus 1, minus 1.5, which is even more negative. The point is it's not going to fire. Okay? Question. So the whole point is you can show that any Boolean function, if it's an OR or an AND, or it's an AND with some negation, you can approximate that with a neural network. Is that clear? So with this kind of network, you can simulate OR. With this kind of network, you can simulate AND. And with this kind of network, you can simulate AND with negations. This is important to realize because, can you tell me why? Why these 3 functions are so fundamental?
They represent like everything possible.
Yes. With this combination, you can represent any possible Boolean function, the universe, and it's called a disjunctive normal form. If you have taken the discrete mathematics class, the whole idea is you can represent any Boolean function as this kind of truth table, right? And this truth table, you'll have some negative and positive values. For the positive ones, you can represent this function as an OR of these positive terms, and each of the positive term is essentially an AND of positive or positive and negative. So essentially, you can represent any Boolean function with ORs of ANDs and ORs of negative ANDs. Then, because we can represent OR and negative and with negative, now we can represent any arbitrary Boolean function, because any function can be approximated with this disjunctive normal form. Okay. So, last couple of slides, we have seen the sigmoid function, right, for our hidden units and even output units. The sigmoid function was nonlinear. It was giving a 0-1 probability kind of thing. We could compute gradients. That's excellent. That's great. But what happens here? What's the problem here? Like as we go along this direction, or we move along that direction, like very far, what happens? What is an issue?
It's just a constant value.
Yeah, so your gradient vanishes. Essentially, your change is so minimal. If you try to compute a gradient, you just get 0. And the whole gradient descent thing is based on gradient. But if you cannot get a gradient, then there is no update. That's kind of a little problem, right? Because the only active region is kind of around here, and then like very quickly, the gradients die out. So to tackle this problem, people have proposed rectified linear units, which looks like this. But then the obvious question is, then again, it's not differentiable here. But we have seen tricks with the hinge loss with functions like this, right? What you can do? How can you compute gradient of this kind of function? Yes? Subgradients, right? So you compute gradient for this part, and you compute gradient for this part. This is just a linear function, so the gradient of this is just 1. And the gradient for this part is actually 0. So magically, you don't even need to compute gradient here. You just need to look at what the value of the dot product is. If it's positive, it's 1. If it's negative, it's 0. You don't even need to compute. And this function can do magic as well. You are not even computing a gradient here. Okay? But this one also has a problem. What is the problem? Let's say you have a big bias term that is negative. So your dot product has to be big positive to make it the overall number positive, right? So this bias term, if it is too negative here, then you need a dot product that makes it even higher than this negative number to make it overall positive. And that may not happen always. Then your neuron will always be in this region. And it will be a dead neuron. It will never fire. Okay? So to address this kind of dead neuron situations, people have proposed leaky ReLU, which is essentially, rather than saying this is entirely 0, add very small gradient to this. So still the neurons are active in that region. It doesn't die out. Essentially, we wanted something like 0 here, but we just give a very small gradient so that it can remain active and participate in the computation of backpropagation, so that there is a hope it will contribute to the process rather than just dying out. Because if a neuron never fires, then it doesn't add anything to your output. Then it doesn't make any impact on your decision. Okay? So this is kind of the end of the lecture, and I think we are on time, which is good. Okay, now I would like you to open your laptops, and we will try to do something. So first of all, let me make some announcements. Okay, so first of all, the neural network assignment is out. How many of you have seen this? Okay, people who don't like to code, the good news is there is no coding here. So you have a multi-layer perceptron assignment where we are trying to ask you, so I have shown you the and, the or, and the negative and, like and with negations. So this one is asking you to do the XOR problem. How can you set some weights? Because XOR is a nonlinear problem, and how do you handle that, right? So this is what we are asking. In the second one, we are essentially asking you to show you can approximate any Boolean function, which I just explained to this class today. You just need to explain it in your own words. And the second part is just doing some homework, some background reading on the different activation functions and loss functions you can try with neural networks. Because there is nothing more in neural network. It's just a connection of units and some loss function and some connections. So I have already shown you 2 different activation functions, right? Can you tell me what 2 different activation functions we have? Actually 3. What kind of activation functions we have already covered? Okay, linear is also one of them. So actually 4, right? So this is, and there is some more like 10H, and just do some Google and Dr. ChatGPT. Like I already said, like you can consult Dr. Google and Dr. ChatGPT for this. There is no harm in this. Just explain in your own words and what are the pros, what are the cons. And then there are some loss functions that you also probably know by this time, like mean squared loss, right? Hinge loss. There is cross entropy loss. I mean, we have already seen entropy computation in decision tree. So you just need to do some more reading about cross entropy. And then there is a binary version of it. There's a softmax version of it. Again, some background reading will make you clear like what this is doing. Just try to explain this. So this should be pretty easy. My idea was to not have you spend a lot of time here. Okay, and then this is the neural network assignment. Any question on this assignment? Okay. So then next there is a bonus assignment. And the idea for bonus assignment is you don't need, if you think like one of the assignments, in one of the assignments your score was very bad or you couldn't even submit, and then this is one chance to replace that assignment with this one. But here the problem is you have to do the reading by yourself. And this is on clustering. This is a new problem, right? And we will not have time to cover this content in this course, but the assignment looks like this. So this is a k-means clustering assignment that I covered last time in this course. So that is again the same assignment. There is a k-means implementation you have to do, and there is a Lloyd method for doing that k-means clustering, and you want to analyze the effect of k, and you want to analyze the effect. So it's essentially there is a famous Lloyd's algorithm to do this. If you are interested in getting like better scores in your assignment, so you should definitely be submitting this, which has a deadline of December 5, and this will help you get rid of one of the lowest performing assignment that you have. Okay. But the question is, how do I know what to do here? So in order to do that, I actually have uploaded the slide in the file section for slides. If you go here, you'll see a new slide called clustering. And then you basically have to read this slide. But then another question is, how do I understand the slide? And then you have my video from the last class, last year, explaining the ideas, okay? I don't know if you can hear it. Probably not. Can you? Oh, my volume is. Right, derivatives. We take the derivative, set it to 0. That will eventually give us the. Oh, it's coming from the laptop, but anyway. We already kind of know that. So if you are interested, the whole idea is you have the lecture related to clustering. So you have the slides, you have the previous year's lecture, you read them, understand it, you have the assignment, submit it. Then you will get your points, and that will be directly added as one assignment and replaced with one of the lowest performing assignments if you are interested. Any question on this bonus assignment? Yes.
Does it require us to like do the same thing like from scratch of every model, or can we use libraries, something like that?
Good question. Last year I didn't allow libraries, but because this is a bonus, I will allow libraries this year. Okay? So yeah, you can use libraries. But I don't know if some of the questions will still remain relevant if you use libraries. If it is no longer relevant, let me know. And then you just need to do the rest of them. Okay? Questions? And there is already a code k-means.zip I have already given. So you probably don't need to code a lot. There is a structure there. You just need to fill in some places. So if you really find it challenging, I will still accept library implementations. Any other question? Good. So the next point is probably assignment is not enough, and you want also to improve your midterm 1 grades. If that is true, then I have something for you, which is called a bonus midterm assignment, which is going to replace, and it has a weight of 60. That basically means if you do it properly, sincerely, will give you 60 points. If you have already scored more than 60 in your midterm, it doesn't help you. Right? If you have not, then you need to sign up for this assignment and let me know. And what this assignment is going to look like is that is something we will have a guest speaker present you. It's just some kind of annotation task for a machine learning data set. So this is more like a data-centric thing, but this is something that only requires your time. It's not challenging. You'll just need to read some text, and you need to make a judgment like how good the output is as a human evaluator. It's more like creating a data set, not actually implementing or something, but it will require some time. I'm expecting you, what should be the expectation, like 10 hours, 5? 5 or lower? Okay, 5 hours is the max that will be needed. And then in that case, if you do it properly, at least sincerely, not there is no proper here, but sincerely, then we will give you 60 points. And that basically can cover for that can be replaced with your midterm 1 grade to help you. Okay. Any questions so far? Yes?
If you have at least a 60, it won't help?
Well, I'm going to take the max.
Okay.
Between what you get here versus what you got in midterm 1. Then it doesn't help, right? Yeah. But if you are if you already have more than 60 in midterm 1, probably you are kind of better than average. That's what I'll say. Yes?
Does it apply to midterm 2 as well, or just midterm?
Midterm 2. Okay, after midterm 2, if you realize you again had a bad score, you can do that. I'm happy to replace with any of midterm 1 or 2. Good question. Other question?
So does that mean that we don't have any more curving?
No, that doesn't mean anything. That just makes you feel good. But it may mean that I don't have carving anymore because the grades are already kind of decent. Right? There is no guarantee. That's what I'm saying. But it will make you feel good that I just didn't give you free points. You did something for it. You achieved. You deserve it. Right? I want you to feel good. about what you got. Yes.
You said sign up for that?
How do we do that? Right. Send me an email, I guess, or send me a private message on Canvas so that I know how many. Because when we distribute the task, how many examples you need to look at and how many you need to annotate, we need to know how many people are signing up actually in the first place. So send me an email. Yeah. Yeah, the other option is I will create a kind of anonymous poll. No, anonymous doesn't help. Yeah, let me see what I can do. Maybe I can get some survey or something set up on Canvas. Yes.
So, but then if we were emailing you, what if we are only worried about our midterm 2 grade? Can we still sign up after that? Or?
Yes.
Okay.
You can. The only my worry is like you probably may not get the grades by like the midterm is on November 30, and then this assignment is due December 5. Like, can we give you the grades by that time? But probably you can guess like what your grade is going to look like, and you can sign up. I don't know. But this midterm is easier. If you have already scored more than 60 in the first one, you are definitely going to score more than 60 in the second one. That's what I think. Okay. No questions so far. So please log into your Canvas and go to the quizzes section, and you will see a survey of this course with 4 questions. Do you see that? Please fill in the survey. I'll give you 2-3 minutes. It shouldn't take more than 3 minutes. This is anonymous, by the way. So feel free to speak up. Again, this is anonymous. Give your honest opinion. How many of you have completed? Okay, so people who have completed already. So you have a next exercise to do, which is to go here, rate my professor. This is again anonymous, right? And you have my number here. Can you see the number? It's 2693422. Let me write it down. 422. Two six 93,422. Yes, that's me. So please rate me. This is anonymous. I'm not going to know.
I think the only course available to rate was Comp 5970.
Yeah, you can create a new course, right?
Thanks.
On Rate My Professor, please create the new course if it doesn't exist. We have some results from the survey. So it looks like more topics would be nice. The course is too demanding, 23%. Strongly agree. There are 8% strong disagree, that's good. Okay. How many of you are still working on Rate My Professor? All right, I'll give you 3 more minutes.
Is anyone able to add a class?
No.
You have to type into the box and then hit create.
Okay. Oh, now it works.
And I will send a survey on the sign up of the annotation assignment for midterm. And for the other assignment, clustering, you can just submit on time, on the deadline, and that's already counted. Once you're done, you can come here and set up like your thing, because at 3:05 there will be 2 other professors walking in, kind of advertising their course on machine learning advanced, like security kind of thing. So we still have 10 minutes. Yes?
I didn't submit my thing, I got an error.
Yeah, I got that too. You just gotta like refresh or go back to something. Do it again, unfortunately.
Okay, sounds good. Because I have never done that, so I have no idea. How many of you have completed both of them? How many of you have completed none of them? Okay, at least one has been completed. Okay, none of them.
But I'm auditing.
You are auditing, yeah, sure, okay, sure. But you can still do the rate my professor thing, if you like. If you want to come in.
Yeah, I'm not sure if I have an example ready, so I can just kind of describe the task.
Yeah, you can describe the task. Yeah, you can just use this board, and I'll give you like what? Yeah, have 10, not 10. Let's say 6 minutes.
Oh, okay, I'll do it quick then. Let's see if I can do this quickly.
So this is. Yeah. I don't have the mic. Go ahead.
Tell me if it's too loud. Can you hear me? Sweet. Okay. Marker. Okay. So this is the task that he was discussing that would kind of combine with your. You would increase your test grade to 60, or you'd increase it possibly to 60. You just take the max of those two. So this is what he was talking about. So this is for. I'm a research assistant under CarMaker, and I'm doing some NLP research, and we are working with taking documents, as in multiple sentences, and they've been shuffled around. And then the goal is to find some models that can take those sentences and put them back in the correct order, i.e. reordering. But we need actual proper ratings of models that have done reordering. So for example, you take the sentences, shuffle them, and you give it to ChatGPT, and you ask ChatGPT, please put these back in the correct order. And the tricky thing is ChatGPT, when it tries to put them back in the correct order, it may manipulate the sentences a little bit. So that means it's kind of unclear how to actually grade ChatGPT's performance. You can't just easily pop out a number on how it actually changed the rankings. You actually need to take into account these manipulations of sentences, and that adds some nuance where we basically just need human examples or human examples of how to rate these. So that's where y'all would be coming in, hopefully. So basically all it would look like is you have document A that's in correct order, so it'll be sentences like A, B, C, D. And then you will be given three other, and this would you do this multiple times. You'd be given 3 other documents, and each one would just be something that would look similar to this, but messed up in some way. Like B could have like have A, but it be messed up, so it's like A prime, then B, and C, D, and then also this model could have like just made up a sentence at the end, and then you could have another one that's just straight up the exact same, or you could have another one that's like it just completely skipped over B. And these would be full-on paragraphs. You have to read the whole paragraph, and you would be kind of in your head doing some labeling like this. And then after you're doing that, you want to rate how each of these documents, how accurately it recreated this original document A. And then you'll be doing that multiple times, and then that's the data we'd be looking for. And then everything would be pretty well explained on the forms we'd be giving you. And then it depends on how many people sign up, but you would be given multiple pairs of these paragraph sets. And that's about it.
All right. Hello. Yes. So if I just rephrase what you said, so your job will be to read first a passage that is in the correct order. Then we internally did shuffle that document arbitrarily and asked ChatGPT and other large language models to fix it back to the original order. But it doesn't know what the original document was. The goal is to understand, can it uncover or can it rearrange sentences in an order that makes sense if we prompt it. And the problem, well, the thing is, we have seen empirically, like by trial and error, like they do a pretty decent job. We just don't know how to like properly evaluate them. What is the metric? And in order to do that, we need humans to kind of look at this task and give us labels. Okay, this is great. This is somewhat okay. This is not good, like this. And we'll tell you exactly in the assignment like what kind of labels to put and how to put it. And we will create a document and release it as soon as possible, right? So that's what we will do. Your job is to look at the original document and then look at, let's say this is GPT, this is Llama, this is another large language model, let's say, Google Bard. And then we'll ask you, tell us how good a job Llama did in reordering the sentence, because you already know what the original document looks like. And based on your labels, we will do some more analysis on that. So this is essentially something like a annotation task, and it's kind of a win-win kind of trade-off between you and me. If you are looking for more numbers, we'll give you more numbers because you'll get 60 points out of this. And for us, we get some annotation that we can use in our research. Okay? Any question on this annotation task? Yes?
It might be a silly question, but how is it going to be graded? Like, how are we going to get graded?
That depends on Hugh, because he's going to combine everything. And depending on how many people are signing up, we will also be looking at the inter-rater agreement. So it's kind of like a team effort. So we will take your annotation and try to see how much you agree among yourselves. If the agreement is high enough, that means everybody did it sincerely, we give points to everyone. If it doesn't turn out to be like a good inter-rater agreement, we'll probably have another meeting with you, like what happened? Let's say there are 5 annotators who agree and 1 annotator who doesn't agree with any of them. Probably that annotator didn't do the job sincerely, right? Or we can have a discussion like, did you have any misunderstanding? And we will give you another chance. So we have a way to evaluate this. And as long as we have you have followed the instruction and you have exactly put the label sincerely, there should be good inter-rater agreement. And that will reflect like, yes, you did your job accurately, sincerely. So that is probably all. So next Thursday there is no class. And then after after the Thanksgiving break, you have a review session for the midterm, and then you have the actual midterm exam, and then after that you have the 2 deadlines, right? For the project presentation, final presentation, and project report. Yes?
Will the review session be posted before the midterm?
The review session is on 28th of November, so that is going to be recorded, right? Like this class.
So it'll be posted immediately?
Yes, so every day we have a class. I think within few hours you have the recording and everything, right? So the slides and the lecture will be online. And on November 30, you are going to sit for the exam. And then again, if you are looking for better grades in your midterm, you should be signing up for this assignment where I will post a survey. And the bonus assignment on clustering is something that you can just turn in on December 5. Everything is kind of around December 5, apart from the final project report, the deadline, right? Everything else. If you haven't yet submitted the surveys on Canvas and on Rate My Professor, please do when you go home. And then in Auburn Canvas, you also have a formal evaluation that will be thrown out maybe in a couple of weeks, and please fill that as well. So those are the evaluation things, and if you are still struggling with the project, you should definitely talk to me, come to my office hour, or you should be scheduling some time on Zoom to really get feedback before it's too late. Yeah, I don't, because I'm still waiting on 2 professors coming in. And that is exactly, they should be walking in any moment. But what they are going to do is, how many of you know Professor Dr. T? So he's walking in. Dr. Springle. Okay, so he's probably walking in right now. Yes, yes, please come in. I have been advertising your names right now, and then I said, like, I'm just going to go out, and the floor is all yours.
Oh, thank
All
you,
right,
thank
so-
you.
Thank you.
Hey, guys. Here, let's.
I'll
You're just gonna shout? Okay.
Let me go out of the way.
Thank you.
Thank you very
Appreciate
much.
it.
Thank you.
Hey, thanks, guys, for giving us a few minutes to talk to you. Maybe you've already seen email about the AI for Security class, but we want to take this opportunity to kind of quickly make a pitch for it and answer any questions you may have. This machine learning class, right? So you guys apparently care about solving ML problems, applying ML to good stuff. Well, guess what? If you're looking for a really cool, hard application domain, security is about as hard as it gets. Is that right?
Absolutely. So the whole idea behind the course is not to take AI people and teach them security. We're not trying to do that. We're not trying to take security people and teach them AI. The idea is, y'all know AI stuff. There's other people that know security stuff. Doing group-based projects that try and combine the two areas. So, you'll learn a little bit about security, a little bit about how we think, how we approach problems, how we solve problems, things like that. But the security people will learn a little bit about, machine learning, about AI, what it can do, what it can't do, and something like that. So using it as a mechanism to apply all the things that you're learning in this course and some of the other courses.
Because if you think about what you're going to do in your career, you're not going to probably have a job where you use ML in isolation. You will almost for sure be on some big team with people from all kinds of domains, and there will be application domain people there, and the hardest thing is not using your ML on that. It is being able to talk to those other people. And even within computer science, like an AI person and a security person talk to each other, that's basically like two different disciplines, right? Very different perspectives to things. And so applying ML, if you are not an ML specialist, right, if the poor application domain person has to do that, they're probably going to misuse it, right? It's really easy to misuse ML. So they need somebody like you on their team, but you need to have enough knowledge of how you can work together with somebody in security in order to solve problems. That's really what the class is about.
Yeah, so it's no exams, no quizzes. It's all project-based. Go out, write some code, figure out where it doesn't work, go write some more code, go fix a model. I don't understand AI. I'm a security person. It's more of the actual going and doing as opposed to the memorizing whatever the concepts and definitions are. It's more of the application.
Absolutely, yeah. No memorizing here. This is more like the real world. You can use whatever you want. Actually, we want you to reuse stuff. This is not about, hey, the first time you've ever done ML model, do everything from scratch. No, this is how do you usefully work together and with minimal code, right? Because in the real world, you try to not reinvent the wheel. Do cool stuff so that you can work more at the conceptual level. And the other thing is, because you're working in the security domain, people are going to mess with your ML. This is all about adversarial thinking, right? So instead of the usual, hey, here's a benchmark, make your ML work as well as possible in that benchmark, it is maybe, they're going to use AI for this. What is the hardest thing we could make? How could we make the benchmark so hard it's going to break your ML? That might not be something you've really thought about.
Can we throw it a corner case that it's not expecting?
Exactly.
But yeah, that's the general thing. It's just the application. But there's information in your email. If you're interested, we'll hang around for a little bit if you have any questions. But yeah.
Actually, one more thing I'll say about it is it's just to give you a little idea of the format of the class. So we're developing it as we go, but it looks like we have 2 sets of assignment series, each one about 4 assignments each 2 weeks. They're all group-based. So the first few, I think, introductory just build you up, but then after that, everything is group-based. So a mixed team, some AI, some security people on each team. The assignments are made so that you cannot solve it if you're only ML people, AI people, or only security people. You have to have that mix. And so there will be pieces where you have to work together. The big underlying kind of thing is a computer network security problem. And so we actually have built a very high fidelity network emulation that you will be working in. And so we've tried to package it so it's nice. You don't have to deal with all the goriness of the world, but it's high enough fidelity that it is realistic.
Where does that data come from? Syslog comes from,
Yeah.
Anyways, yeah.
So that's it. Any questions for us?
All right, cool.
So
Oh, so
either they're all signing up or they're not interested.
They're taking advantage of the 4 minutes we're giving them back.
All right.
No, all right. We'll be
Oh,
around.
there's a question.
Yes, sir.
I actually just had a general question, not a question about the course. I'm curious because I just went to visit Frontier, or I went to Oak Ridge National Lab to visit Frontier, and I'm wondering, like, how much do security problems scale with huge systems like these and very complex networks?
So how much does security problems scale? Exponentially. Because you've got somebody that's building your front end, your UI. You've got somebody that's building your core logic. You've got somebody that's building your database interactions. It's hard enough getting any one of those to actually be resilient, secure, private. But now you have to start putting the pieces together, and the different interactions are where you get the really interesting, complex bugs that turn into major vulnerabilities. But that's part of what this is trying to do. One of the things AI is great about doing is scaling. You know, if you've got a terabyte of data, you can build a model on something and run 10 terabytes worth of data through it. Assuming a lot of AI complexity I'm going to ignore. But, you know, AI is one of the advantages, has one of the advantages of being able to scale. Security people, we don't scale very well. We still have to sleep, we still have to eat. And, you know, with AI, it takes so much time and energy and focus to actually understand how to do that well. With security, it takes so much time and energy and focus to understand how to actually build instincts and build the mindset and all the background. Trying to figure out, okay, can we apply some of the concepts across? As opposed to, well, go do a PhD on security and then go do a PhD on ML and hope that your security PhD hasn't gone completely out of date.
So this is not related to the question asked, but for some reason this made me think of another thing to mention about the class. Almost every other class you'll see at the university, you've got a set of prereqs, every student's the same set, right? That's not going to be the case here, because we've got security people, we've got AI people in the class. So basically when you look at it, you'll see it's a whole bunch of classes with ORs. You can any of those. And so,
including this one?
Including this one,
Yeah.
absolutely. So there's several AI classes you could be in. So it's really hard to know what we're going to have. So the way we're building it is it's pretty autonomous. There will be little lectures to kind of introduce you to whatever AI concept we're going to use. So there will be some classic ML. There will be some evolutionary computation. There will be some neuroevolution. We're going to look at the trade-off between performance, like really high performance ML, often can be very hard to interpret, versus maybe an approach that's much easier to interpret, but maybe not quite as high performant. And so we're going to look at that in the context of solving security problems. Oh, that just came to mind. Other questions? Yeah.
So you mentioned that it would be hard. Did you mean like hard volume-wise, like there's going to be a whole lot of work, or hard conceptually?
I didn't say hard, did I?
I thought you had. I don't know. I might have mistaken that.
Really? Walk in the park.
It's definitely not going to be the easiest because it's a group-based project. It's go and write code. Your code's not going to work, or it's not going to work the way you want to. Go debug it. But it's not intended to take your life, if that's what you're asking.
Yeah. So it's not going to be.
absolutely not.
Yeah. This is good. Average hardness, I would say. I think the hardness, looking back, so we have taught this once before, kind of a precursor version, is not so much the algorithm. To me, at least, and Dr. Springer may have a different opinion, but my impression was that the hardest thing is for the team to learn to work together. The AI and security people being able to communicate effectively with each other to solve the problem was the hard thing. So it's not like a ton of math or something like that. We don't want math. We want to solve problems.
And you get to use a lot of the software engineering concepts, because this happened this morning. We were talking about feature selection and feature extraction, his definition of feature is totally different from what I was treating as a definition of feature. So it's a lot of, figuring out, okay, here's how we need to talk about it, here's how we need to set it up to make this project work, so we can turn it in, so we can run it and show that it works.
Because doing ML, when you're given a nice data set, hey, here's your data set, go apply this. Oh, look, that's the result you should expect. Wonderful. Then you get to the real world, and they're like, data? Yeah, there should be data. There's a system. First, figure out how to get data out of it. Get it in the right form. And you may not even fully understand it. And if you put the wrong data into ML, you'll get an answer, but it's not a useful answer. So there's a lot of problems in actually cleaning it up, pre-processing, figuring out what data actually matters, doing the feature selection and all that, and then interpreting the answers you get out of the model. So this gives you an exercise in a semi-real world setting. Yeah, great question. Yeah.
Is this already on Tiger Scheduler?
Yes.
Yes, 59, it's one of the 5970 special.
Yeah, special topics. The 005, 5970, 6970, 005, and there's also a synchronous distance section. Other questions? No? Hey, we'll hang around here for a little bit.
We'll hang
Thank you.
around, but thanks for taking the time. I still have any questions.
Yeah.